Hello, greetings. We're back in lab for another lab. This is Titration Gyration, and we're going to do some titrations. Russ Gnome is here. He's been actually a great helper because I actually did a bunch of titrations already. I'm going to just show you one of them. And so the idea of titration is in our burette here. So this is a burette. You see the whole thing, this gorgeous burette. It's filled to the zero with silver nitrate. So burettes were designed by gnomes, and they actually make a lot of sense. The volume, when it is full, tells you how much you've added. So it's at zero right now because we've added nothing. So once we add, we just read what the number is, and that's our volume. All right, so in the first part of the lab, I wanted to very precisely, meaning to 4 sig figs, determine the concentration of the silver nitrate. And so I used very pure, sorry, I lost it. I think I put it away. I used very pure sodium chloride. Mountain Community College has not skimped on me for 25 years. We have 100.3% purity sodium chloride. Can't get this at Fred Meyer's. 100.3%. That's really good lab analysis there. Anyway, so it's pure sodium chloride. And I measured it out on analytical balance, which are very special balances because they go to 4 decimal places. They go to 1/10 of a milligram. And so they're actually in a special place in the lab. Our lab that they built the chemistry lab on the 2nd floor doesn't really make sense, but the analytical balances have to be placed over solid ground because they're spring balances. And if there's any vibration, which there always is, just a little bit of vibrations, then the scale wiggles too much. And so I get to get a little bit of exercise. You would have too in the lab. All right, so then come back, add a little bit of water. I did 3 samples and add our indicator. So our indicator has a yellow hue to it, and it's potassium chromate. And so when you add the silver nitrate, the nitrate, Nick, swims away. He doesn't care. But what is in here, and the sodium, it swims away. And the other cations that would be in our solid swim away. But the silver and chloride, oh, they have quite the interest in each other. So as I'm titrating, we're going to see like a yellow or a white. It actually eventually becomes a very beautiful white precipitate forms, very milky white, until we hit the point where every chloride has bonded and precipitated. And then the next drop, there's no more chloride. So the silver finds something else, and it finds the chromate ion. And chromate and silver, they make this color. And as soon as we start seeing a different color from either the slight yellowish color, we start seeing actually a peachy color, because that's the first drop. If I keep adding, it does get to this color, and I'll show you that. That tells us the chloride has all bounded, done its thing. There's no more chloride, and we stop. We take a measurement, and we can do math. So titration is where the stoichiometry, the endpoint, the color change, is where everything is stoichiometric perfect. It also allows for precision. Burettes are actually quite expensive because the gnomes very precisely gave us measurements. So we can read to 4 sig figs. Graduated cylinders only allowed 3 sig figs when we did the density lab way back. So let's go for it, and then I'll show you all the data I have. And I'm very excited because it's been decades since I've actually had to titrate. Usually I just, watch you all titrate and give you advice. You want to be my lab partner this time, except for Damon, because as he said, he and I would just talk too much and we'd miss the end point. So, and if we're fortunate enough to be in lab this summer, we get to do several titrations, so you will become quite proficient at these. And apparently it stays with you your whole life. All right, so I know, because I've already done these other ones, that I'm going to be adding 30 milliliters. So I'm going to go ahead and add 30 milliliters pretty rapidly. Oh, we're at 13. You can see the color. So let's see. Can you see the color? Yeah, you can see it's getting like, you can see the yellow. It's actually going to get milky white. The yellow is just because it was colored, but you can see it's getting cloudy. It's like a milky color. It's getting cloudier. We're going to slow this down. Yeah, and you can see it's like this beautiful, it's a whitish color. It has maybe a yellowish hue to it, but it doesn't have this peachy hue yet. So we haven't gotten to the point where the chlorides, there's still some chlorides in there. The silvers and the chlorides are still doing their dance. We're going to slow down adding them. And if you look where it adds, when you see the drop hit, you can see an orange show up, but then disappears as we keep mixing. It means we're getting close. And so, getting close, we can slow it down. Okay. Oh, it might be too slow. You see the yellow, the reddish show up and disappears. And keep going. Slow motion. Anticipation. Isn't there some commercial about that? I think it was the ketchup commercials in good old days, where they're waiting for the ketchup to come out, waiting for the color. It does become, we don't want that ketchupy color. We're going to read our volume before that. It's such a rewarding lab because you're going to know you have really good data. And we're going to go through the calculations together. Not all of them, but enough. I also want to remind you, in class, should be on Tuesday, we are going to do a sample calculation for Part A and Part B of the lab. So you remember they're there when you do your calculations. Getting there. This would usually be where my TA, you can see the color. The color is definitely changing. We're like one more drop. That was it. So that is our peachy color. I'm looking for a piece of white paper. You can kind of see we definitely have a peachy color now. So let's get our volume. Oh, it's reading the bottom of the meniscus. If you zoomed in on your camera, it'd be so exciting. And it's just a hair below the 36. So we can go with 36.05. You're going to have all the data up on the board, but I want to show you one more piece. I just have to write that number down. Yeah, let's go with that. All right, what if we kept titrating? What if we went, oh, we turned it the wrong way. Oh, well, that, that's like we missed the end point. What if we really missed it? Oh my goodness. It just keeps getting darker and darker, and that's what this was. If we go back to the other side, so I can dress the color of the lab, I know some of you might appreciate that. That was the color we were going for. So convenient to have that. Yeah, not good. All right, let's turn the noise off. Let's look at the data. So you can pause and write down our data. So I got our masses for Part A, and these were the volumes. And all the titrations went to that beautiful peachy endpoint. The color of our skin. So where we had just the first hint. So if you were doing it, I tell you to write that. And this one we did get our volume before I added 50 mils, everything that was in there, because I have to clean up after this. All right, so our masses in the first part were the pure sodium chloride, and in the second part, we had an unknown. We can call it J for Joyce. So this was our unknown J. If you want, you can make it unknown Joy, right? Let's be joyous. And then these are the volumes of the silver nitrate that I added for each one of these. These beautiful data tables. Organized, right? It's not a long list. It's okay, this is part A, this is what we had. Now, I actually did some calculations. I crunched some numbers for us for part A because I want to go through parts per thousand. So how to get to this molarity? Using, right, the mass. We start with the mass of the sodium chloride because the sodium chloride's known. Now in part B, you cannot start with the mass because we don't know what J is. J is not on the periodic table. Although I'll tell you this, in Mendeleev's original periodic table, in the Russian alphabet apparently, I doesn't happen. I is actually written as a J, so iodine was actually J. It took me years. I'd be teaching in class, and I was like, I can't spell my name with the periodic table. It was so sad. But it turns out I can with the letter I, because it's really a J. Iodine's really a J. Go figure. There you go. That could be your bonus for this lab. Yes, I had so many bonuses, really. Spell your name with the periodic table. What elements would spell your name? Can you, like, my last name was easy. All right. So we take the mass of the sodium chloride, change its moles, right? Using our periodic table, adding up the sodium and the chloride. And we want molarity. So remember, molarity is moles per liter. So that gets us to moles of sodium chloride, but then we do a stoichiometric ratio of 1 to 1 because silver and the silver nitrate and the sodium chloride react in a 1 to 1 mole ratio. So that gives us also our moles of silver nitrate, but we want moles per liter. So we need to divide by the volume, changing it to liters. And we're allowed 4 sig figs, and I actually did pretty good. So you will have to show your math. I did 3 samples because I'll tell you what, I was wondering, what if I mess up? I want to make sure I have a 3rd sample, but I didn't. So we're going to use all 3 of these samples. And so you will show your math. You should get pretty similar numbers. It really depends how you round your periodic table. 0.05. Remember, the zeros are not significant. They're placeholders. And you can show the 0 before if you like. I'm going to switch to the black pen because I think it shows up better. All right, you're going to add the 3 numbers together and you'll get an average. And I put down my average somewhere. I believe we get an average of 0.05186 for using my numbers. I want to make sure you know how to do this. Now, in part B, the calculations are different. You're going to start with the volume, changing it to liters, doing this in a flow, changing it to liters. You're going to multiply by this average, which gets us to mole. Then we know it's a 1 mole to 1 mole ratio of the silver ion and the chloride ion. Because by the time you do this lab, we'll have talked about net ionics. The sodium ion doesn't matter. And Nick's the best swimmer of us all. All right, so that gets us to chloride, and then we will eventually divide by our unknown mixture times 100. Now, our unknown is a mix of a whole bunch of different salts. It is not sodium chloride. It's not potassium chloride. It's not lithium chloride. It's a mix. And somebody very precisely figured out the percent. And so you'll do the calculations. We'll do it a sample in class, so you'll be able to go back, make sure, and you'll do this. But what I want to show you is the error analysis for part A. To know that I did really good, well, I can see this is a lab of precision. I repeated, and I got really close to the same number. My first 2 digits here are 5, 1, and then a high digit after that. And so I averaged them. Now, we're going to do what's called the deviation. And I want to make sure you understand this, because not all of you come to my office hours. And that's because a lot of you cannot. And so I recognize that. So deviation is found by taking the average, which I got this number when I averaged my data, minus the data point. But there is a but, because a lot of you don't read my notes quite right. Those lines there mean absolute value. So you will always get a positive deviation. We do this different. We are doing an average deviation. In statistics, you do something called standard deviation. Now, standard deviation, you just always get this number. It can be a positive or a negative. And then you square it, you add them all together and take the square root. And that's wonderful. In chemistry, we do it a little bit different. And we're in chemistry right now, so you'll do it my way. And when you take statistic, you can do it their way. And then when you go and get a job in the real world, and if you do deviation, you'll do it whatever way your job wants you to. It comes out similar enough. You don't have to go and nag the little chemistry teacher and tell her she does her math wrong, because we do it our way. Okay. Yeah, you can tell I have a pet peeve. Being a small person, people like to tell me I do things not right. But, all right, so the idea would be the 0.05186. It has a unit, molarity minus or 0.0569. Whoops, 5169. And you do this for each data point, and you'll get a deviation. And they're really small. Now, be careful, because there's lots of zeros. So this one is like 0.00017, 0.000, because it's absolute value, so it comes out positive 13. And this one's got even more zeros, 0.00003. So these are my deviations for my data points. Can't tell if you can see me. And then what we're going to do is we're going to average those deviations. So this average was for this, 0.05186 molar. Now we're going to average these. So you all know how to average. You just add the numbers together and divide by how many there were, which is 3. All right, and so we add them together and divide by 3, and I get 0.00011. Now, one more step. There is a page in the lab that walks you through this, that you take the average deviation. It's something that's actually quite useful. Divide by the average, and then we're going to times by 1,000. So basically what we're doing here is we're seeing how close our numbers really are to each other. And so it's something that chemists call parts per thousand. We only do this when we have multiple data points, which is in titration. And what we're looking for is ideally under 20 is good. If you're in lab, you do need to be under 10 to not lose any points. Tell you what, you want to be under 5 is awesome. And so you take this, right, my 0.00011, and we divide it by the 0.05186. Now, none of you are here to answer my question. We should be respecting units. Our deviation does have units of molarity. In part B, when you get your numbers, will be percent. And so at this point, though, the molarity over the molarity will cancel, times 1,000, and I get roughly 2. I have a note. You can put 2 sig figs, because we have 2 here, so 2.1. That's really good. I would be so stoked if I was you and have data like that. Now, when you do this part of the lab, I crunch numbers real quick, and I don't know why I do things backwards. You can analyze me. I know these two come out really close. They're going to come out somewhere in the 58-ish%. So you should get around 58% when you do your calculations. I haven't crunched this number yet. Maybe we should crunch it real quick. How we did it all together. Oh no. There we go. What's my average? So on part B, we start with the volume. We multiply by our average from part A. So we standardized with a known sodium chloride. We know very precisely our concentration. And what we're going to is not sodium chloride in part B, but just the chloride. All we care about is the chloride ion. We don't know what cations are in there. It's a mix of them. And then we divide by our unknown and times by 100. So we get a percent. And yeah, they all come out really close. They all come out really close. They're all in the 58% range. And then you're going to do the average. You're going to do deviations, average deviation. You're going to get your parts per thousand again. Tell me how I did. Under 10 is good. Under 5 is awesome. 2 is fantastic. All right. You're also, okay, don't tell any of my colleagues this. I'm going to tell you the answer for J. I can tell you it because it's not actually J. I didn't give you the real number. But I looked up what the answer is and the actual percent. After I'd done my calculations, I was really stoked. You guys never get to know what the answer is, but you're graded on it. So you can tell me how I did. You're going to do a percent error for me. The actual is 58 point, make sure I get it right, 36. For unknown J. J for joy. So you can actually do a percent error besides parts per thousand, and then you're going to tell me how I did. Yes, I was precise because all my data comes out really close in part A and part B. I got the right color. I didn't get that awful, the Rasta color, right? You know what's really cool? I don't know if any of you know this, but since it's Sherpa Tibetan New Year this week, I don't know if you know, but the Tibetan flag is the same flag as the Rasta flag, the Jamaican flag. And so I actually used to get to tutor some Tibetan monks many years ago, dear friends, and they were fresh off the plane. They didn't speak a word of English. And some of them never spoke a word of English, but he and I could communicate in other ways. And I did not know it was Tibetan New Year. So I went to tutor them, and it was always so exciting to be there. And it was Tibetan New Year, and so they were making me food, and everybody's there celebrating. And they were all listening to Bob Marley, and they knew how to do the dance. So, all right, Daniela will appreciate that story. Anybody else who's a Rasta fan? You'll tell me how accurate I was, how close I am to the actual. You'll get to do a percent error. And then you're going to do some post-lab analysis. So let's talk about the post-lab analysis, because I know it's harder because you're not in lab, but to tell you the truth, students always didn't take much time to think through. They never really did great with post-lab analysis. All right. If you end the titration when it was white, because you were so excited it was white, you didn't add enough volume. Now that's going to give you a different calculation in part A, where we divide by the volume, right? So if you didn't add enough volume in part A, so you're dividing by a smaller number, it's going to give you a larger answer. But in part B, we would be multiplying by the volume. So if you didn't add enough in part B, you would actually get a smaller answer. So you can ponder that. Now, if you're so excited, you got distracted by a mermaid, a fairy, the Rasta gnome, or you're just like the Rasta gnome and you really dug this color, means you added too much. So how would that affect it? And so you will have to explain that in a very careful and concise way. Does it make your final answer too high? So if it's an error in part A, you'll have to first say how it would affect your molarity, and then the molarity, how that affects your final percent. If it's an error in part B, you just say how the math would affect your final percent. All right, and then it will ask How does it affect your parts per thousand? If the color's wrong, your parts per thousand are going to be terrible because you did it wrong. But if it's a systematic error, like you just always, I don't know, something was wrong with the sodium chloride, the purity of the sodium chloride was not the 100.3%, well, that's a systematic error. And so that's not going to affect your parts per thousand because all of them are going to have that same error. But a color, that's a random error. You just weren't being careful enough. All right. Well, I'm wishing you all happy New Year. We get to celebrate together on Thursday, and I'll see you soon.